Dear students, Assalamu alaikum. So in the previous lectures we discussed various parameters of the dimensional analysis. We discussed the dimensions, what are dimensions, what's the dimensional formula, what's the dimensional equation, and we derive various dimensional formulas of various fundamental quantities as well as derived quantities. After that, we solve some numerical problems on the basis of use of dimensional analysis. So in the previous lecture, we solved some numerical problems on the first use of dimensional analysis, that was to convert one system of unit into another system, such as we convert uh, uh, SI system into CGS system, we convert 1 Newton into dynes, we convert 1 Joule into ergs, etc. Now, our today's topic is, that is, we will also solve some numerical problems today, but on the second use of dimensional analysis. Now, our second use of dimensional analysis, that is to check the correctness of the physical relation. Now, while solving the numerical problems on this use, we have to go through these three steps. Number one, that is write the dimensional formula. We have to write the dimensional formula of each physical quantity involved. Number second, then we will apply the principle of homogeneity. And number third, if the dimensions on both sides of the physical relation that is same, so we can say that it is dimensionally correct. Now, so I choose some numerical problems which are very important. They are usually asked in the examinations. So our first numerical problem, that is S equal to ut plus 1 divided by at square. That's also known as the equations of motion. It's the second equation of motion. So we'll solve this numerical. Our question is S is equal to ut plus 1 divided by 2 at square. So we'll follow these steps. Step number one, that is, we'll write the dimensions of each physical quantity which involved this physical relation. We have here, number one, we have here S. That's the distance. Basically, these equations of motion, they give the relationship between the velocity, acceleration, or distance, as well as time. So here we have S. S is the distance. So that means a length. So we'll write in this way. We have to write the dimensional formula. So we'll write in this way. It is L. That means in this distance, mass is absent. So we'll write here m0. L is present by one time. So we write it as L1 and T0. So it's a dimensional formula of distance. Number second, we have a U, that's the velocity. Velocity means displacement divided by time. So that is written in this way, L divided by T. So we'll write here, so mass is absent here. So we'll write here m0. So L by one time and T is also by minus one time. So this is the dimensional formula of velocity. Then we have 1 divided by 2. So this 1 divided by 2, it is dimensionless constant. Dimension less constant. So it's dimensionless constant. Then we have acceleration. Acceleration A. So we know the acceleration, velocity divided by time. So we'll write here velocity. The dimensions of velocity, they are m0, L1, t minus 1 divided by time. So we'll write here t1. So acceleration, dimensions of acceleration, they are m0, L1. So this will be t minus 2. So this is the dimensional formula of acceleration. So it was the first step. This was the first step. Now in the second step, we apply the principle of homogeneity. So we have the equation here, we have the relation. Relation first. We'll write the dimensions of each physical quantity which is involved in this physical relation. So we'll write here S. So S, that is equal to M naught L1 T minus T naught. T naught. That is equal to U. So U is M naught L1 T minus 1 into T1 plus 1 divided by 2, that is dimensionless. So we'll write here the dimensions of acceleration M naught L1 T minus 2 into T square. So we'll write here T square. So we'll solve this relation. We'll solve these. M naught L1 T naught. So this is the LHS side of this physical relation. That is equal to, here we have M1, M naught L1 T minus, no, it is T naught. So here it is T raised to power minus 1, T raised to power 1. So will be T naught plus here. So M naught L1 T minus, so here will be T naught. So T raised to power minus 2 and T raised to power 2, it will be T raised to power 0. So we'll apply the second step, apply the principle of homogeneity. So principle of homogeneity states that if the dimensions of the fundamental units of the physical relation, but on both the sides, if it is same, so we can say it's dimensionally correct. So we'll see here LHS side as well as RHS side. So dimensions of the fundamental units, they are same. So we can say this is dimensionally correct. Here we say, so we can also apply the third step. If the dimensions on both the sides of the physical relation that is same, so that means this physical relation, it is dimensionally correct. So we say here this physical relation, it is dimensionally correct. Similarly, we can solve the various numericals. We have V equal to U plus AT, number second numerical, and number third we have V square minus U square equal to twice AS. So we can also solve on the basis of the correctness of the dimension analysis. We can solve these numericals.